In this lecture, we're going to move on to symmetric matrices and their applications. And this particular lecture can be thought of as an introduction. So we're going to define what we mean by a symmetric matrix, and also we're going to calculate the so-called eigenvalues and the eigenvectors of these symmetric matrices. Now, symmetric matrices have important properties and very, very nice, simple characteristics. And in particular, we're going to use the methods that we'll see today down here when we want to solve, for example, systems of ordinary differential equations. Okay, so the first question is, what is a symmetric matrix? Well, suppose we have, say, a square matrix with, we're only going to be interested with, in matrices with real components. We call A a symmetric matrix if A and A transpose are the same. Now, just to remind you, when I take the transpose of a matrix, I interchange the first row with the first column, the second row with the second column, and so on. So you can see here I've got a 2 by 2 matrix, 2 rows and 2 columns. What I can do to form the transpose is take that column, the first column, and write it as the first row. I take the second column and write it as the second row. So the transpose of this would be this matrix here. Now the transpose has some nice properties, which I've just outlined down here. In particular, if you take the transpose of the transpose, then you return the original matrix. And if you take the transpose of the product of two matrices, so A, B all transposed is the product of B transpose with A transpose. Now, notice, just remember that the order is important. When you multiply two matrices together, the order is important. Okay, so A times B, where A and B are matrices, is not necessarily equal to B times A. Okay, well, when I'm given a matrix and I want to look for whether it's a symmetric matrix or not, I sort of look at the diagonal. Okay, so here we've got a 3 by 3 matrix, and I look down the main diagonal, this one from left to right, and you can see actually, well, this is like a line of symmetry here because you've got some reflection going on. So the 0 is reflected here, the 2 is reflected, and the -1 is reflected. Here's a smaller matrix. Again, we form the main diagonal, and we've got a reflection of the -2. Now, these are two examples of matrices that are not symmetric because there's no line of symmetry down that main diagonal. Now, symmetric matrices, like I said before, have important properties that we will look at and use to solve several kinds of different problems. Okay, so when I write E values and E vectors, I mean eigenvalues and eigenvectors. Now, just for the first part here, let's just, we will be interested in calculating these things for symmetric matrices, but let's just put a general definition down first. Suppose A is a square matrix. Here I've got n by n. That's probably not necessary. And suppose that this equation holds for some number, lambda, possibly a complex number, and for some vector, v. We call the number lambda an eigenvalue of the matrix A, and we call the vector v a corresponding eigenvector of A that corresponds to the lambda. Now, you'll see here that if v is just the 0 vector, well, this will be satisfied, but we ignore that case. We call that the trivial case. So let's have a look at a basic example. Here's a 2 by 2 matrix, which is not symmetric, and we're given the following information. Or we're given, well, I guess the following claim. We claim that the eigenvalue 3, lambda equals 3, corresponds to the eigenvector v equals 1, 2. So what I would like to do is take that 3, take that vector there, and see if this is satisfied for this matrix A. Well, let's look at the left-hand side. If I take this and multiply, okay, 1 times 1 plus 1 times 2, that gives you 3. 4 times 1 plus 1 times 2 gives you 6. I can take a common factor of 3 and factorize it, so I've written it as a number, 3, times a particular vector, 1, 2, this vector here and this number here. So yes, 1 does hold. So this eigenvector corresponds to this eigenvalue. Now, you can also see that, hopefully, that if I just multiplied this vector by, say, 2, then that would also correspond to this eigenvalue. So any multiple, any non-zero multiple of an eigenvector is also an eigenvector. Okay, so here's an example for you to try. Show that the eigenvalue lambda equals -1 corresponds to this eigenvector and this eigenvector for this matrix. Okay, so essentially just repeat the steps here. Okay, so we are going to be interested in how to determine the eigenvalues and the eigenvectors when you're given a real symmetric matrix. So to do this, what we're going to do is rearrange this. So bring the lambda v to the other side. And then what I can do is insert this matrix I, which is a special identity matrix. And essentially it's just got zeros everywhere, and down the main diagonal is 1s. And the identity matrix is a little bit like the number 1. If you multiply any matrix or vector by the identity matrix, then you just get what you started with. Okay, so I can replace this with this, and then I can factor out a common factor of this v here. Okay, so now I've got like a system of equations here, a homogeneous system, and I'm going to concentrate on this coefficient matrix, the A minus lambda I. Now, if that coefficient matrix A minus lambda I has an inverse, in other words, if the determinant of that's non-zero, then the only solution to this problem is a trivial solution, and we're not interested in that case. So what we do is you sort of flip it on its head, and we wish to determine the values of lambda for which this coefficient matrix fails to have an inverse, which will happen when the determinant's just 0. So to determine the eigenvalues, lambda, of A, we solve this equation here. So instead of writing out det for determinant, sometimes I just put these absolute value or sort of vertical lines in. Now, of course, it's not absolute values because these are matrices, but it's usually clear from the context what's going on. Okay, once we have the lambdas that solve this, we go back systematically for each lambda and solve this equation for your eigenvectors v. Okay, so by the 0 over here, of course, I mean the 0 vector. Okay, so let's do some examples and see how we go. Okay, compute the eigenvalues and the eigenvectors of the following symmetric matrix. So we're going to work essentially with this coefficient matrix here. So A minus lambda I is essentially just insert a minus I down the diagonal. And we're interested in the determinant of this matrix and when it equals 0. So the eigenvalues can be found by solving this equation here. It's a 2 by 2 determinant, so I multiply diagonally. So it's that times that minus that times that. Okay, so I end up with a quadratic equation, and it's just a simple way of factorizing or solving. Here we've got the difference of two squares, so I can just sort of break that up and come up with the following. So I know that lambda is either -1 or +3. So I found two values for lambda, and what I would like to do is compute the corresponding eigenvalues, the corresponding eigenvectors for each lambda separately. So let's do that. So what we want to do is solve this for each lambda, and let's discuss the cases separately. Okay, well, for lambda equals -1, a minus lambda I, so just put -1 in there for lambda, I'm going to get this coefficient matrix. So if I expand that, or just look at it, it's 2v1 plus 2v2 equals 0. So I've got two equations that are telling me the same thing. If I simplify, say, the first line, I'll get v1 equals minus v2. So now all sorts of values of v1 and v2 will satisfy that bottom right-hand corner. So what we can do is just choose one value and get the other value from it. Okay, so these choices to make simple choices. So, maybe choose v1 equals +1, and you can get v2 from that. And that's exactly what I've done. So I've made that choice. You could make other choices. Of course, you wouldn't want to choose v1 equals 0. That would give you the 0 vector. Okay, so once we know these components, I can just write it out as a vector. So let's look at the case lambda. So this then is the eigenvector corresponding to this eigenvalue. So let's look at the case lambda equals 3. So essentially we want to solve this just with lambda equals 3 for v. So we go up here, plug in lambda equals 3, and I'll get this matrix here. So the first line is going to give me something like 2v1 equals 2v2. So I can simplify that. And similar to this one, I'll get some sort of relationship between v1 and v2. So again, I'm just going to choose either v1 or v2 and then get the other one from that. So I've chosen v1 equals 1, so v2 equals 1, so I get the eigenvector corresponding to this eigenvalue. Okay. So that was pretty easy because it's a 2 by 2 case. We're just solving quadratics, and the equations here are not, or the environment here is not too challenging. So let's look at the 3 by 3 case. This is a little bit more time consuming. So here we've got a symmetric matrix. We're asked to compute the eigenvalues and the eigenvectors associated with A. So let's write down the coefficient matrix, A minus lambda I. We get this. And we want to look for the values of lambda such that this matrix doesn't have an inverse. In other words, when the determinant's 0. So we need to compute the determinant of a 3 by 3 matrix. This can take a bit of time. So just out of habit, what I like to do is just expand along the top line. Okay, now there's a 0 in the top line, so that's a good sign. That's going to simplify a lot of calculations. Okay, so essentially to expand a 3 by 3 determinant, you go to the first entry in the top line, and that first entry is in the row and column that I've covered up, and you multiply the first entry by the determinant of what's left. Then you move on to the next one. You cover up that, and you'll multiply that number by the determinant of what's left with a minus sign. Then you move on to 0. Cover up the row and column and multiply 0 by the determinant of what's left. Okay, so if I do that, that's going to be my first determinant. That's going to be my second determinant, not forgetting the minus sign here. And then the 0 is going to act on the determinant of that. So that's not going to give us anything. Now remember for 2 by 2 determinants, it's just multiplying diagonally appropriately. So I'll get down to something like this. Now you can simplify the algebra there, and I'll get some sort of cubic, and I can just see, well, remember this thing's equal to 0, so lambda equals 0, well, lambda squared minus 2 equals 0. So I'm going to get 3 eigenvalues. 3 eigenvalues. So now what I've got to do is discuss each case separately and find the eigenvector that corresponds, or an eigenvector that corresponds to each of these values. Okay? So that's the idea. So let's discuss the case lambda equals 0 first. Okay, so if lambda equals 0, I can go back up here and replace lambda with 0. So that's my coefficient matrix. And essentially what I want to do is try to calculate v1, v2, v3. So if I look at the first row, 0 v1 plus 1 v2 plus 0 v3 equals 0. Well, that tells me that v2's got to be 0. The same with the bottom row. That tells me v2's got to be equal to 0. The middle row, 1 times v1 plus 0 times v2 plus 1 times v3, that tells me v1 plus v3 equals 0. So from that combination of information, what I want to do is come up with some sort of eigenvector. Well, v2's got to be 0, and if I choose either one of these, I can get the other one. So I've just chosen v1 to be 1, so v3 will be negative v1, negative 1. So this is an eigenvector that corresponds to this eigenvalue. All right, well, that's one case. Let's have a look at the case lambda equals positive 2. Again, this is my coefficient matrix. It's not so easy to see how to come up with v1, v2, and v3 in this case. Sometimes you can do a bit of row reduction here or elimination if you want to write them as systems of equations. What I can see here is there's a 1, a positive 1 and a positive 1 sort of there and there. So if I take row 3 away from row 1, these 1s are going to cancel. Okay, and I'm going to get something like root 2 v1 equals root 2 v3. In other words, v1 equals v3. Now the middle row is going to give me 1 v1 minus root 2 v2 plus 1 v3 equals 0. So based on these two pieces of information, let's see if we can come up with an eigenvector. Well, I've gone over here and I've chosen v3 to be root 2. Now, I've just chosen root 2 there because the numbers work out a little bit sort of more rounded than in some sense. You don't have to choose root 2. Okay, so if v3 equals root 2, v1's got to be root 2, and then I can plug these and get v2. Okay, so I can write this as a vector. That's my eigenvector. And the last case is lambda equals minus 2. So I won't discuss that, but it's very similar, and you can come up with an eigenvector like that. Now, here's another example. Okay, you want to pay attention now. This is going to make the trip all worthwhile. Okay, it's going to make the trip all worthwhile. We're asked to compute the eigenvalues and the eigenvectors of this 3 by 3 symmetric matrix. Okay, now this is a special case, and it's a case where you solve solve for the lambdas, the eigenvalues, but they're repeated in this case. Okay, so this has to be taken with a little bit of care. And we'll see that as we go along. So let's consider the coefficient matrix A minus lambda I. So it's going to be something like this. And what we would like to do is determine the values of lambda such that the coefficient matrix fails to have an inverse. A minus lambda I fails to have an inverse. So that will happen when the determinant of this is 0. Okay, so again, you might want to sort of try to save some space here because I'll probably go over the page for this one. Okay, so for the eigenvalues, we're going to solve this. So It's going to be a 3 by 3 determinant. Okay, so again, I'm just going to expand along the top row. So minus lambda times the determinant of what's left, minus 1 times the determinant of what's left, plus 1 times the determinant of what's left. Yep. Okay. So now expand these 2 by 2 determinants, and then we'll try to simplify in some way. Okay, so again, you just work diagonally. So it's minus lambda times minus lambda minus 1 times 1. So that's going to be lambda squared minus 1. Okay, minus 1 times minus lambda minus 1 times 1. So that's going to give me something like this. And the last one, 1 times 1 minus lambda times 1. So I'm going to get something like 1 plus lambda. Lambda. Okay, so the tempting thing here is to, the object here is to simplify this in some way. We're going to have to simplify this. So you can do that in a number of ways. What I like to do as a general rule is not expand the brackets until I really have to. Okay, so wouldn't it be good if you sort of saw this and there was a common factor here, here, and somewhere in here? Okay, then you could immediately solve, simplify. Okay, so in fact there is one. Okay, there's a 1 plus lambda there. You can take the minus sign out and make that into a 1 plus lambda, and you can factorise that into a 1 plus lambda. Okay, yeah, pretty good, huh? So you don't want to just necessarily expand those brackets all the time. So let's take out a common factor of, say, lambda plus 1. Because remember, this is lambda squared minus 1. That's just lambda plus 1 times lambda minus 1. Okay, so I'm just going to clean up what's in this square bracket now. Yep. Yep. Plus lambda. Okay, so now this is a quadratic inside the square brackets. I can factorise that again. Just to make it a little easier, so I've got a positive lambda squared, I'm going to take a common factor of minus 1 out the front. Okay, so if I take a common factor of minus 1 out the front, I can come up with the following factorisation. Okay, so now we're in a good situation because we can get our roots. Lambda's either minus 1, positive 2, or negative or minus 1. Okay, now you can see that I've got a repeated root. Lambda equals minus 1 with a multiplicity. It's like a repeated root. Okay, so how do we cover that case? How do we cover that case? Okay, well, let's discuss the case lambda equals minus 1 first. The case lambda equals positive 2 is reasonably straightforward. So this is part 2 now, where we're calculating the eigen vectors. So for each lambda, solve the following. All right, so let's discuss the case lambda equals minus 1. Okay, well, when lambda equals minus 1, I'll just get a sort of diagonal of positive ones here. So I get a matrix that just involves positive ones everywhere. So we're going to get 3 equations that tell us the same thing. Okay? Is anyone still going down here? Okay. All right. So all right, so we've got a system of 3 equations here that are essentially the same equation. So let's just take, say, the first row. And I'll get V1 plus V2 plus V3, oops, V3 equals 0. Okay, so this is the equation of a plane. Let's choose 2 values in that boxed equation to get the third. So I've labelled this as equation E, just E for equation. Okay, so what have I chosen? In this particular case, I've chosen V1 to be 1, and I've chosen V2 to be 0. Now, you don't have to make those choices. They're just really simple choices. So for these choices, what's my V3 going to be? -1. Okay, so it's going to be 1, 0, -1 as my eigen vector. But I can make another choice, say V1 equals 0 and V2 equals 1. Well, in that case, if I put those in here, V3 is going to be -1 again. So, what I've produced here are 2 linearly independent eigenvectors corresponding to the eigenvalue lambda equals -1. Now, if you look at these 2 eigenvectors, they're not orthogonal. Okay, they're not orthogonal. But I could choose them to be orthogonal if I wanted to. And I'll give you an example of that in a minute. Okay, so that covers the case lambda equals -1. Case lambda equals 2. So let's go up here and we're going to get something like the following. Okay. So I look at this and I go, well, it doesn't seem like that's an easy system just to look at it and go, oh, okay, I can choose V1 to be this or V2 to be that. So what I'm going to do on this one is actually do a bit of row reduction. Okay, now remember with matrices and systems of equations, you can add multiples of rows together and take them away from each other and whatnot to simplify. Okay, so I'm going to do the following operations, right? So firstly, I'm going to get this number up here to a 1 just by interchanging the first row and the first column. Sorry, the first row with the third row. Okay, so when I put this arrow that goes both ways, I mean I'm just sort of switching the rows. So I get something like this. Okay, so what I would like to do now is get all the numbers under this 1 in the top left-hand corner, all these numbers to be 0. So I can do that just by taking, say, multiples of the first row away from the second row and the third row, or just adding, if you like. So I'm going to do that. Row 2 is just going to go to row 2 minus row 1. And row 3 is going to go to row 3 plus to row 1. Okay, so if I do those calculations, I'll get the following. Okay, so you can see those two bottom rows basically tell you the same thing. Okay? Now, the first fair bit of information, but the second and third rows are just telling you the same thing. So we obtain the following. So V1 plus V2 minus 2V3 equals 0. And the second and third rows tell us V2 equals V3. Okay, so what I'm going to do is choose V2 to be 1. I'll get V3's 1, and I can get V1 from this equation up here. So I'm just squishing it in here. My eigenvector will be 1, 1, 1. Okay, so they are the corresponding the eigenvectors associated with the eigenvalues. Now, I said before that these two aren't orthogonal. Okay, but I can actually go back and choose them to be orthogonal if I want them to be. Okay, so let me show you. And I'll show you in a minute. Anyone still going with this one? Okay. Yes?
It says if V1 equals 1, then V3 equals 1 and V1 equals 1. Or V2.
Oh, sorry. Yes, thank you. Let me fix that up. Sorry. So I've chosen V2. Let me just adjust that. V2 to be 1. I can get V3 from here and then get V1. Okay, thank you. Okay, so I mentioned that these aren't orthogonal, but I can choose them to be orthogonal. I'll come back to that in a second. Okay. Now, a couple of important observations. I'm not going to prove these things, but hopefully you can get a feel for what's going on with the 2 or 3 examples that I've given you. If you look back at every example, each of the eigenvalues were real numbers. There were no complex numbers in there. The corresponding eigenvectors all had real components. Now, the eigenvectors associated with distinct or different eigenvalues are orthogonal to each other. And I claimed, okay, and this last bit might not be in your notes, so make sure you have this down properly. I claimed that if I compute, say, 2 eigenvectors and they're not orthogonal, I can actually go back and choose the eigenvectors to be orthogonal. So let me show you what I mean when we have a repeated eigenvalue. Okay, so it's true in general for, these observations are true in general for every symmetric matrix with real entries. Okay, so what do I mean when I say 4? Well, in the previous example, okay, so the one that I just did, these were our eigenvectors. But I could have chosen them to be these eigenvectors. Okay? And if you look closely down here, these eigenvectors are orthogonal to each other. Okay? So when you're doing these questions, it will be important that you choose the eigenvectors to be orthogonal. So that is something that you should test when you're doing these questions. Okay, computing these eigenvectors, are they actually really orthogonal? If not, you can always go back and choose them to be.